Hey folks, welcome to DevLayer. In this video, we are breaking down the solid principles with simple explanation and code examples. Before we dive into each principle, let's talk about what solid actually means. So solid is an acronym for 5 core principles of object-oriented and clean software design. These principles help you write code that's not just functional but also easy to understand, maintain, extend, and scale. Here's what it stands for. Together, you can use these principles to create a strong foundation for building modular, flexible, and robust code. Now let's break each of these principles down with clear examples and visuals. Let's start with the first one, that is Single Responsibility Principle or SRP. This one is all about keeping your code focused and maintainable. The rule here is simple, that is a class should have only one reason to change. So you can think of a class as a worker. If the worker is doing too many jobs, it becomes chaotic and fragile. For example, imagine you have a user manager class that is responsible for creating a user, sending an email, and also logging user activity. That's way too much. If any of these responsibilities changes, the whole class has to change. This is hard to test, hard to reuse, and even harder to maintain. So a better design is to separate these responsibilities into their own classes. So we can have a user creator class, a logger class, and an email sender class. Now each class does one thing. So if the email logic changes, you only touch the email sender class. And if logging needs to be updated, you update the logger class. So the responsibilities are isolated, and this makes your code easier to understand and maintain. As a real world analogy, you can think of how things work in a restaurant. A chef cooks, the server delivers food, and the cashier handles payment. So if one person was assigned to do it all, mistakes would happen very fast. But when each role is clearly defined, the system runs smoothly. That's what SRP is all about. Clear roles and clean separation. The second principle is the open close principle. This means your class should be open for extension but closed for modifications. The core idea is you should be able to add new features without changing existing behavior or code of your class. For example, imagine you have a discount calculator class with a getDiscount method that takes in user type as a parameter and returns the respective discounts. Now let's say there's a business requirement to add a new user type of platinum. Now you need to go inside this method and add in another if statement and then another and another. So you are now constantly modifying existing code every time business logic changes, which is too risky because we could accidentally break the logic for existing user types while trying to add new user. A better solution is to design your code to be extendable so that we can add a new behavior without touching what's already there. Here's how we can do that. We can create an interface called discount strategy with a method getDiscount. Then create separate classes like gold user and silver user, which can implement these discount strategy classes. Now, if we want to add a new platinum user, we can do that very easily by implementing the same discount strategy classes, all without touching any of the old code. So this is super important in large code bases, which can help you to build plug and play logic that can scale without any side effects. Now let's talk about the Liskov substitution principle or LSP. It means a subclass should be replaceable by its parent class without breaking the program. In simpler terms, if your code works with a parent class, it should also work with any of its subclasses without any surprises or errors. Let's take a better real-world example. Say you have a class vehicle that has a method refuel. A petrol car extends vehicle, which is expected as it also refuels with a petrol. But then you have an electric car which also extends vehicle. Now what happens if you call the refuel method on the vehicle object and the vehicle object is an object of electric car? It throws an error. Therefore LSP is violated. The fix is to use abstraction, specifically interfaces. Instead of forcing all vehicles to implement refuel, we can separate the responsibilities into different interfaces. We can have a refuelable interface with the refuel method and a chargeable interface with the charge method. Now our petrol car can implement the refuel interface and our electric car can implement the chargeable interface. We only call methods that make sense and substitution can be safe. So our code becomes cleaner, more accurate, and less error prone. So the key takeaway here is that we shouldn't force a subclass to pretend it can do something just because the parent class does it. Subclasses should be a true logical extension of the parent, not a workaround. If the behavior doesn't make any sense, we should use interfaces and separate the responsibilities. Next up, we have the interface segregation principle. The rule is pretty simple here. The classes shouldn't be forced to depend on methods they don't use. Imagine we have a worker interface with two methods work in it. Suppose you create a human worker class implementing this interface. It has the work method implemented with the work logic and the it method implemented with the it logic. This should work fine, right? But what happens when you add another class called robot worker implementing the same worker interface? In case of robot, the it method cannot be implemented, right? So what you can do is you can just leave it unimplemented or you can throw an error, both of which are very bad designs. The better way is to split the interface into smaller, more focused ones, each representing a single behavior. So we can have a workable interface with the work method and the itable interface with the it method. So our human worker class can implement both of these, and in case of our robot worker, it can implement only the workable interface. This way, each class only commits to the behavior it actually supports. So this might feel like a small thing, but it makes a huge difference in large systems. When our interfaces are too big or generic, they become fragile. So we should always try to keep our interfaces small, focused, and behavior specific. Finally, we have the fifth principle, which is the dependency inversion principle. So this one is very powerful, especially when we are working on large code bases. So what it says is high level modules shouldn't depend on low level modules, both should depend on abstractions. Imagine you have a user service class and inside it you directly create an object of MySQL database. Now this user service is tightly coupled to MySQL. Let's say if we want to switch to MongoDB, we'll need to rewrite the full user service. This breaks flexibility and makes our testing harder. A better design is to invert the dependency. Let user service depend on an interface, not a specific class. So we can have a database interface which can be directly used inside our user service class. And this database interface can be implemented by our database classes. This is exactly how dependency injection frameworks work under the hood, like in Angular, Nest.js, or other frameworks. The key takeaway here is that we should never hardcode dependencies inside our classes. Instead, we should define interfaces and let the actual implementations get injected. And that's a wrap on the solid principles. These 5 simple but powerful ideas can truly transform how you think about writing code.